In this video, we're going to talk about a number of different important topics to set theory. We're going to talk about the set of infinite binary sequences, the real numbers again, and we're also going to make use of Cantor's diagonal argument. What we did in the previous video was demonstrate an explicit bijection between the natural numbers and the rational numbers. And our conclusion from that video was that the rationals are countably infinite. And what we're going to do this time is we're going to eventually show that the set of real numbers R is not countably infinite like the rationals were. And the terminology we're going to use is that not countably infinite is going to be uncountable or uncountably infinite. And our strategy in this video is going to be threefold. First, we're not going to deal with the real numbers first, but we're going to deal with the set of all infinite binary sequences. And what we're going to show is that this set of infinite binary sequences is uncountable. Then what we're going to do is we're going to match up each of those infinite binary sequences to a real number in the interval 0 to 1. And by 0 to 1, I mean on the number line, just the numbers from 0 to 1. And then what we're going to do is we're going to stretch out the interval 0 to 1 to include all of R. And in terms of the workload, the biggest hurdles are going to be steps 1 and 2. Step number 3 is fairly simple. In step number 1, we're basically going to make use of Cantor's diagonal argument. Step 2, we're going to set up a clever bijection between the binary sequences and the 0 to 1 interval. And then in step 3, what we're going to do is we're just going to apply the tangent function to stretch out this 0 to 1 interval to all of R. So let's get started. Let me first introduce a piece of new notation here. So let me consider two sets, the set 3 and the set 2, where the 3 and the 2 are understood to be the set theoretic 3 and 2. The set 3 is going to contain 0, 1, and 2, and the set 2 is going to contain the numbers 0 and 1. Now, the new notation I'm going to introduce is going to be this thing here, which I'm going to read as the set of all functions from 3 into 2, where that superscript 3 means the domain of the functions, and the 2 is going to be the range of the functions. So what that means is that if you can think of a function from 3 into 2, that function has permission to be in the set 3 into 2. So this is going to be clearer through examples. So let me give you two examples of functions that are going to be within the set 3 into 2. The first one I'm going to call f1. By way of reminder, a function is a set containing ordered pairs. So f1 is going to be, for example, the set containing 3 ordered pairs, 0, 1, 1, 1, and 2, 1. Now this is a function from 3 into 2, because let's visualize this as arrows, as drawing arrows. 0, 1 means I'm mapping 0 to 1. This ordered pair 1, 1 here means I'm drawing an arrow from 1 to 1. I'm mapping 1 to 1. And the 2, 1 ordered pair means I'm mapping 2 to 1. So that's a first example of a function. And a second example is going to be also 3 ordered pairs, but this time 0, 0, 1, 1, and 2, 0. And again, if you want to visualize these as arrows, 0 gets mapped to 0. That's what that first order pair means. 1, 1 means that the 1 gets mapped to 1. And a third order pair, 2, 0, means that the 2 gets mapped to 0. So hopefully you can see that f1 and f2 are functions mapping 3 into 2. Now another piece of notation I'd like to introduce. Instead of writing the 3 order pairs here in the set, I'm just going to list those second components there. Because you can see that these first components are just being repeated. It's sort of understood that each of these things, 0, 1, and 2, is going to get mapped to something. And the only question is what it's getting mapped to. And instead of writing out these ordered pairs as 0, 1, 1, 1, and 2, 1, I'm just going to write out a binary string. In this case, 1, 1, 1. And by binary, I mean that the string contains either a 0 or a 1 in any place in that string. So I'm going to represent this collection of 3 ordered pairs, not as the ordered pairs explicitly, but 1, 1, 1. And hopefully you can see why, because the 1, 1, and 1 are the second components there. And likewise, f2 is not going to be written like this, but it's going to be writing out those second components, 0, 1, 0. So I'm going to represent f2 as this binary string of length 3, 0, 1, 0. And hopefully this notation is pretty natural. You can see why this is going to clean up the notation a bit. Now, since I'm concerning myself with binary sequences of length 3. That means that this set, 3 into 2, is going to have 8 possible functions, or 8 possible binary sequences. And I've got those listed out here, F1 through F8. And just to make sure that we've understood ourselves, here are the possible binary sequences of length 3. And you can see here there are 8 members. And more generally, hopefully you can observe this, the set n into 2 is going to list out all of the binary sequences of length n, where n is understood to be some finite number, some natural number. For example, 100 into 2 is going to list out all of the binary sequences of length 100. And naturally, that set is going to have 2 to the 100 members. Now that we've seen a couple of examples of this new notation, let me set up the formal definition here. We're going to say that the set A into B, where again the A is written as a superscript, is the set of all functions from A into B. And just to generalize as well, if A has n elements and B has m elements, A into B is going to have m to the n elements. At this point, we're ready to consider the set of all infinite binary sequences. And this is why I set up that notation before. So now what we're going to do is we're going to consider this set omega into 2, where again, omega is a set of all natural numbers, and the set 2 is the set theoretic 2, which is going to be the set 0 and 1. And again, we're going to consider all those sequences which map omega into 2. So already, if you like to visualize these things, we're drawing arrows between each of these elements in omega to something in 0 and 1. So you could map 0 to 0, 1 to 1, 2 to 0, 3 to 1, and so on. You can imagine those arrows being drawn. And now, the important distinction here is that these binary sequences are now going to be of infinite length. For example, I might have the set containing all these ordered pairs. Now it's going to contain infinitely many ordered pairs. It's going to contain, let's say, 0, 1, 1, 1, 2, 1, 3, 1, and so on. And this set is an example of something that would be in the set omega into 2. Now to write this out in our different notation using the binary strings, I just write those second components there, 1, 1, 1, and I'm going to tell you that all these are going to repeat on to infinity. So the 1, 1, 1, 1, 1 means that 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, and so on. That this element, this object here, is going to be an element in the set omega into 2. And another example of some infinite binary sequence that's going to be in omega 2 is going to be the sequence which has zeros repeating on to infinity. And another one would be 1, 0, 1, 0, 1, the alternating 1, where the bits alternate onto infinity. That would be another example of something in 0 to 2. So hopefully you can get a sense of all the things that are going to be in omega to 2. And this set here, this is just the previous alternating binary sequence written out in the ordered pair notation. And these would be some of the things that would be in omega 2. So already you can see this is a very, very complex set. This is not like something we've dealt with before. It has infinitely many elements, and each of the elements has an infinite length. So already we're going to see the complexity of this set. This is why it merits very careful treatment in set theory. Now that we have at least some idea of what the set of infinite binary sequences looks like, let's now investigate some of the mapping properties to and from this set. Now the claim is, I'm going to make this claim here, that every natural number can be mapped to a unique infinite binary sequence. And the way I'm going to demonstrate that is every binary sequence can mark the natural number which maps to it with a 1 in that position, and then zeros in every other position. To make that explicit, I'm going to say that the natural number 0 can be mapped to the infinite binary sequence 1. I stick a 1 there because 0 is going to get mapped to 1, and then zeros elsewhere. So that 1 indicates, or it stands as a marker, that 0 is being mapped to that infinite binary sequence. And likewise, the infinite binary sequence 0, 1, 0 is repeating out, stands for the fact that 1 is being mapped to that sequence because the 1 is in the 1 position. And continuing on further, I have the 0, 1, 2 position, and the 2 position has that 1 there, and that 1 marks that 2 is being mapped to that sequence. And hopefully you can see the pattern there, where the natural number, which maps to that sequence, has a 1 being inserted into that position. And what's the significance of all this? If you think about the sizes of these sets, hopefully it should make sense that this set omega into 2 can't be smaller than omega, because this set of infinite binary sequences has enough room to accommodate all of the mappings coming from these natural numbers. That is, every single natural number has some designation within this set of infinite binary sequences. That is, it can be marked in this set. So it should make sense that this set can't be smaller than omega. So in an intuitive sense, the size of this set, or eventually we're going to say the cardinality of this set, is either going to be equal to or greater than the set of natural numbers. So that's sort of the intuition behind first writing out this injection from omega into 2. And this is what I've just said here. What I've demonstrated here is an injection, an injective function from omega into the set omega to 2, which is a set of all binary sequences, set of all infinite binary sequences. One important thing to point out from this whole mapping that I was talking about here is that this mapping that I found from the natural numbers into the set of infinite binary sequences is injective but not surjective. And it's not surjective because in this mapping it's very easy to think of examples of infinite binary sequences to which no natural number maps. For example, let's consider the sequence, instead of 1 zeros repeating out, let's consider the sequence 1, 0, 1, and then zeros repeating out. In this mapping, there's no natural number that corresponds to that. Therefore, this mapping is not surjective. But it is injective because if I give you any infinite binary sequence of this form, where it's zeros in all places except one place, you can tell me which natural number maps to that, which basically means it's left invertible. I wanted to point out that distinction between the injective functions from omega into set of all infinite binary sequences and the surjective properties, because really the meat of the Cantor diagonalization argument is a statement about the fact that there are no surjections between these two sets. It's very easy to think of injections, but the force of this statement of the theorem is that there is no surjection, let's call F, from omega into the set of all infinite binary sequences. And since there are no surjections between those two sets, there are no bijections. And basically, this is the statement of the theorem here. And now let's use the diagonal argument to demonstrate this. Now, this is the standard proof of the uncountability of this set. And the way it's going to work is by contradiction. Now, the theorem says there are no surjections, let's call them F, from omega into omega to 2. So a proof by contradiction is going to say, let's suppose there is some surjection F. And what I'm going to do is I'm going to show you that that surjection fails to be a surjection. That is, how do we demonstrate that some function is not surjective? What we do is we identify some element in the range here, some element, some infinite binary sequence here, and then I demonstrate that no natural number maps to that one that I just picked out. So the strategy here is going to be to identify a counterexample infinite binary sequence. And if you can understand that statement to identify the counterexample, then you've basically understood the mechanics of this proof. So what I'm going to do, I'm going to introduce another piece of notation here. We're going to keep the bits of the binary sequence abstract when we're talking about mappings from the natural numbers to the binary sequences. What that means, if I have some infinite binary sequence here, let's call it S naught. And that's going to be, let's say, 1, 0, 1, 0, 0, 1, 1, 1. Instead of writing it like this, I'm going to identify S0, 0 as being equal to 1. So the S0, 0 means it's the 0th element of S0. Then S0, 1 is going to be the first. It's going to be the number in the first position, or the bit in the first position. Then S0, 2 is going to be that 1 there because it's in the 2 position. Then hopefully you can see what's going on with S0, 3 and S0, 4. For example, I can write this sequence S0 as in the bit form, S0, 0, S0, 1, S0, 2, S0, 3. And if I had some other infinite sequence, let's call it S1, I could write that out as S10, S11, S12, S13, and so on. So this is just another piece of notation here. And notice that in this notation, what I mean by S sub n means that n, that natural number n, is going to be mapped through f to some sequence S sub n. And this will become clearer when we set up this table here. So what I'm going to do, as I said in the proof, I'm going to consider that the fact that there might be some surjection from omega into the set of all infinite binary sequences. And what I'm going to say is that 0 gets mapped to some sequence, 1 gets mapped to some sequence, 2 gets mapped to some sequence, and so on. And using the notation I introduced before, the sequence being mapped to 0, or that 0 maps to, is going to be designated by S00, S01, S02, S03, and so on. And the same notation applies for all the other natural numbers. For example, the sequence that gets mapped to 2 is going to be written as S20, S21, S22, S23, and so on. So I'm considering, because this is a proof by contradiction, that such a thing can happen, that such a mapping exists. And now what I'm going to do is I'm going to identify some binary sequence, some infinite binary sequence that cannot be in the range of f. And to do that, this is what's called the diagonal argument. I form a new infinite binary sequence, let me call it S star, which is going to have as its bits the negation of S00 in the first position, well, not the first position, but the 0th position. In the first position, it's going to have the negation of S11. In the 2 position, it's going to have the negation of S22, and so on. And what that corresponds to visually is reading down the diagonal of this table and negating each of the elements that I read down the table. And then forming that new binary sequence S star. And again here, this squiggle means that you replace a 0 with a 1 and a 1 with a 0. So that's what I mean by negation, that you flip the 1s and 0s. Now clearly, S star, this new sequence that I've identified, that's clearly in the set omega to 2. This is an example of an infinite binary sequence, which means it should be, it is in the set omega to 2. However, S star cannot be in the range of f. So that's the key statement right there. Can you identify where on this table S star is to be found? So let's go through the table. Is it found here? Could 0 be mapped to S star? No, because if you consider this sequence here and S star, they're clearly different because S00 differs from the negation of S00, which means that S star cannot be this sequence here. Now, could 1 be mapped to S star? For the same reason, no, because this sequence here differs from the constructed sequence in this position right here, in at least that position right there. The sequence could conspire to be identically the same everywhere else, but we are guaranteed that it's different in that location there. Therefore, 1 is not being mapped to this S star. And you repeat the argument all the way down. Since S star differs in at least one place, no natural number listed here can be mapped to S star. Now that's really the key statement of this proof, that by the construction of S star, no natural number could conceivably be mapped to this. Now to give you an example of how this style of proof would play out, you might visualize this, as we've been suggesting before, as a conversation between two people. Now one person claims that they can match up every natural number to an infinite binary sequence bijectively, which means injectively and surjectively. And then the second person says, okay, why don't you write out that bijection right there? And so they write it out, and they have it here on this table here. And this table would continue down infinitely. And then the other person says, okay, I'm going to show you where your mapping fails. And what they do is they read down the diagonal here. In this case, they're going to read diagonal 0, 1, 1, 0, 0, 0. And then they're going to flip everything on you. They're going to say, okay, where is the following S star on your table? And of course, the way they've constructed that S star is by negating all the bits there. So we read 0, 1, 1, 0, 0, 0. So they're going to consider the S star to be 1, 0, 0, 1, 1, 1. And then the other person who set up this mapping has no reply to that. They can't find it anywhere on their table because they're looking through their table and they say, is it S0? Well, no, because S star is clearly different from this S0 here. They then go down to S1. It's different here in at least that position there. It's different from S2. They keep going through the table and they can't find which natural number maps to S star. And this is really the force of the statement here, if you can understand how this situation is being played out. And so at this point, what we've done is we've established that there are no bijections from the natural numbers to the set of infinite binary sequences. And so we say that omega into 2 is not equinumerous to omega. Having established the uncountability of the set of infinite binary sequences, we can now translate our findings to not just that set, but now translate our findings to the set of real numbers. So our next task is going to be to map each one of those infinite binary sequences to some real number. And first, we're going to restrict ourselves to just the interval 0 to 1. And essentially what we're going to show is that the interval 0 to 1 is uncountable. And then secondly, this is going to be the step 3. As I said, we're going to extend the interval 0 to 1 to the set of real numbers in general. So first we're going to find a bijection between the infinite binary sequences and the interval 0 to 1. Now a very simple thing to do, and a very effective thing to do here, is to stick a point in front of the binary sequences. For example, if I give you the infinite binary sequence 1, 1, and 0 is continuing, notationally I just stick a point in front of that. And then I read this object here as a number. Now I'm not going to read it as a decimal number, but I'm going to read it as a binary number. So the 0.11 there, where that all this stuff occurs after the decimal point, it doesn't mean 1/10 plus 1/100th. What it means is 1/2 plus 1/4. Now this is how I'm going to read that in binary. And if you're unfamiliar with this, this is very easy to look up. And you can understand this in 5 minutes. Just reflect back on what the notation means for decimal and extend that to binary, where this first position here means 2 to the minus 1. And then this position here means 2 to the minus 2, which translates to 1/2 plus 1/4, which means that this binary expression here, with a point in front of it, is going to stand for 3/4. And correspondingly, this 1, 1, 0, 0, 0 repeating is going to stand for 3/4. We could just map that to 3/4. And as another example, the infinite binary sequence with all zeros, if I stick a point in front of that, right there, we can just associate that to 0. And another example, the binary sequence with all ones, I stick a point in front of that right there, and I read that as 2 to the minus 1 plus 2 to the minus 2 plus 2 to the minus 3 plus 2 to the minus 4, and so on. and I get this infinite series here, which hopefully, converges to 1. So what that means is that this object here and this object here are going to stand for 1. I'm going to associate those or map those two objects to 1. Now this is going to take care of most of the work here. Now the only problem we need to take care of is the repeating 1s problem. In decimal, this is the repeating 9s problem. In binary, it's the repeating 1s problem. If I consider this binary sequence here, 1 and then 0s repeating after, I could just associate that to 1/2 just by sticking a decimal point, or not a decimal point, but a point in front of that. However, I have this other infinite binary sequence where 0 is in that 0th position, and then 1's repeating afterward. If I stick a point in front of that right there, I read off this new number here, 0.011111 repeating. I write that out, and that also goes to 1/2. This is equivalent to the problem of the number 1 being equal to 0.99999 repeating. So the problem is here I have two infinite binary sequences, this one and this one, which I'm going to want to say stand for the same thing, namely 1/2. Fortunately, what we can do is we can list out all of the problematic binary sequences and then cleverly create a bijection to get around this problem, to map those infinite binary sequences into the interval 0 to 1. In my opinion, this is the wackiest part of this video, this problem that you have to get around with repeating 1s, but you have to do it if you want to make the statement that the real numbers are uncountable. You have to deal with this problem with the repeating 1s. Unfortunately, that's not too difficult, but hopefully I can be coherent here. Now, the fractions which are associated with the repeating 1s, those problematic objects, can be listed out. And those are just fractions like 1/2, 1/4, 3/4, 1/8, 3/8, 5/8, 7/8, and then 1/16. And hopefully you can see the pattern here, that these denominators are just multiples of 2. And then once I've established the denominator, I just go up by 2's if I can. For example, after 1/16, the next object here would be 3/16. And then the next one would be 5/16 and so on. But the point is I can form this collection A, this sequence here, which lists out all the problematic objects here. Now let me consider this other object here, A star. Now these are going to be the same things, except these are going to be the infinite binary expansions which are not associated with repeating 1s. That is, this first object here stands for 1/2, but it's going to be the 1/2 without the repeating 1s after. It's just going to be 1 and then 0s repeating. And then the next thing here, 1/4, I write that here. This is going to be with that 1 in the second position with the repeating 0s after. This is the representation for 1/4 without the repeating 1s. And then this next sequence here, this is going to be the representation without the repeating 1s of 3/4. So hopefully you can see the pattern here that I'm listing out all the problematic ones, except in the set A star here, I'm listing out the expansions without the repeating 1s. So this expansion here is the non-problematic one for 3/4, then 1/8, 3/8, 5/8, and so on, where these are understood to be binary as usual. Now what I can do is I can also list out the problematic sequences, the ones with both the repeating 1s and the repeating 0s after. Now the first one I'm going to list out is the repeating 0s, which is going to eventually stand for 0. I'm next going to list out the one that I want to be associated with 1, which is repeating 1s. And then what I'm going to do is I'm going to list out both of the expressions for 1/2. So first I list out the expression for 1/2 with repeating 0s, and then the expression for 1/2 with repeating 1s. So hopefully you can see this pattern here. I have the two possible ones for 1/2, and then after 1/2 comes 1/4. Then next I have the two problematic ones for 1/4. This one here is going to be the one with repeating zeros, and this one here is going to be the one with repeating ones. Then what's after 1/4? It's 3/4. Here's the expression for 3/4 with repeating zeros after. Here's the one for 3/4 with repeating ones after. And then I list out the two expressions for 1/8, the two expressions for 3/8, the two expressions for 5/8, and so on. So as I said, this is a little wacky, but hopefully you can understand where this is going. So now what I do is I associate all the elements in B with the corresponding element in A star, maintaining that order there. That is, this first object here is going to be lined up with that. It's going to be mapped to that first object here. That second one there is going to be mapped to the second one there. This third object is going to be mapped to the third object here, and so on. Now notice what's going on here. I have that expression for 0 with repeating zeros. That's going to get mapped to the expression corresponding to 1/2. And also notice that the expression for 1 is being mapped to the expression standing for 1/4. And this is why in this mapping, I'm going to be taking those numbers 0 and 1 and mapping them to numbers within the interval 0 to 1. So that's why I put those open, why I write this as an open interval here instead of a closed interval, because the numbers 0 and 1 are being essentially stuffed into the interval. So now, let me sort of compile all of the information we have here. I'm going to call this mapping from the set of infinite binary sequences into 0 to 1, G. Now, G is going to be given piecewise. Now, if X happens to be the nth sequence in B, if it's the nth sequence here, if it's one of these bad sequences here, what I'm going to do is put 0 point, and then I'm going to stick in the nth sequence in A star. For example, if X is equal to, let's say, the repeating ones here. Now this is in the second position in B. I'm going to map that to the thing in the second position in A star. I'm going to follow that pattern there. I'm going to follow that mapping there. If X is the nth sequence in B, that is, it's one of the bad sequences. And if it's not one of the bad sequences, that's very simple. I just put 0 point in front of it. Now, as I say, this whole G function thing is a bit wacky, but it absolutely has to be done in order to make sure that we're using bijective functions only. Now, just to make sure you've understood what's going on here, take some examples of binary sequences which are both problematic, that is, they're found in the set B, and ones which are not problematic, such as the expression for the square root of 2 in binary, and see if you can tell me which number in the interval 0 to 1 they're getting mapped to through G. And if you can do that, then you've understood what's going on in this G function. And also see what the numbers, what the infinite binary sequences with zeros repeating and ones repeating get mapped to. But conceptually, what's going on here is what we wanted to do is we want to send all of the infinite binary sequences to a unique real number in the interval 0 to 1. That's all we want to do. We just want to find some mapping, namely some bijection between the two. Now, to complete the proof that the reals are uncountable, what we now have to do is take those numbers in the interval 0 to 1 and bijectively map them into the entire set R. Now, of course, this is a small, well, fairly small subset in R, and what we need to do is stretch it into all of R. And fortunately, everyone's heard of a function which does something like this. It takes a subset of R as its domain, and it stretches it into all of R in its range. And this would be the tangent function. Now, I say this because if you look at the tangent function here, what it's doing is it's taking this open interval, negative pi over 2 to pi over 2, and it stretches it into the entire real number line. That is to say, everything here gets mapped to a real number, and any conceivable real number gets mapped to from something in this interval, negative pi over 2 to pi over 2. And this is precisely what we need to stretch out this interval. Instead of using negative pi over 2 to pi over 2, we need to convert this interval to 0 to 1. And fortunately, that's not difficult to do. We just use our basic function transformations. So just playing around with these intervals, what we need to do is move that negative pi over 2 to 0. And how do you do that? You just shift to the right by pi over 2. And when you do that, what do you get? You get the interval 0 to pi. Now to convert 0 to pi to the interval 0 to 1, you just scale down by 1 over pi. And writing all that out, let's call this final transformation h, which takes the interval 0 to 1 into r. H of x is going to be given by the tangent of the following function, which encompasses both those transformations that shift to the right by pi over 2 units, and the scaling down by pi. Scaling down by really 1 over pi, by multiplying by 1 over pi. And we're going to call that final bijection h. And there should be no problem seeing that this is indeed a bijection, that the tangent function operates as a bijection. And I now claim that the function composition h of g is going to do what we intended it to do. It's going to take the set of all infinite binary sequences and take it to R. Because remember that G takes the set of all infinite binary sequences into the interval 0 to 1, and H takes the interval 0 to 1 into R. So I finally claim that we do indeed have a bijection between omega to 2 to R. Quite a bit was accomplished in this video, but let me summarize what we've done. We started with the set of all infinite binary sequences, and we first showed that the set of all infinite binary sequences was not equinumerous to omega. That is to say, it was uncountably infinite. Next, what we did is we established a bijection between omega to 2 and the set of real numbers, and the bijection is given by h of g. And I claim since h of g is bijective, the set of all infinite binary sequences is indeed equinumerous to the set of all real numbers, which basically means they're both uncountably infinite. And combining this statement here, omega to 2 is equinumerous to r, and also that omega to 2 is not equinumerous to omega by the transitive properties of the equinumerous relation, we finally have the statement that r is not equinumerous to the set of natural numbers, which is to say that r is uncountably infinite. And that'll conclude this video. Thanks for putting up with me with that hopefully somewhat coherent explanation of why the real numbers are uncountable. And if you have any questions, please leave them below. Any comments, also leave them below. And I suspect I'll get more comments than usual in this video, just because this topic tends to make a lot of people angry. The fact that the reals are uncountable, that tends to anger people for whatever reason. So please leave your angry comments below if you'd like to. And here are the two practice problems for this video. This first one is pretty interesting, so I'd recommend if you're interested in this topic, give this one a shot. It's also very conceptual too. And feel free to subscribe and stay tuned for more videos. Thanks for watching.